Alright, now our brute force approach was big O of n cube in terms of time complexity because it consisted of two stages. The first stage was trying out each and every subarray, and we have used two nested for loops for this, and we can say that the time complexity of this is big O of n squared. And the second stage was of course checking if that subarray is a palindromic one, which was big O of n. Now, as you know from the arrays chapter, in these types of problems in which we try out each and every subarray and we want to compute an information for that subarray or check if it respects some property, one optimization we often do is use the fact that when we want to compute that information for a subarray, we have already computed this information for the previous subarrays, right? So, when I try to compute the information for the subarray ij, for an example, right, I can use the fact that previously, on the previous iteration, I have computed the information for the subarray I and j-1. There were some problems in the arrays chapter where this was super important because the only difference from these two subarrays is of course the new element nums of j. For example, if we needed the sum of each subarray, of course we could have used the fact that we have already computed the sum for this subarray and we can only increase the sum by nums of j. But here, unfortunately, knowing whether this subarray is a palindrome or not is not that useful in order to jump to this subarray and tell if it is a palindrome or not. And think about this scenario. Let's say the subarray I and j-1 was A, B, C, B. This is not a palindrome, so the only information we have after checking this subarray is, let's say, a boolean false. It's not a palindrome. That's all. Now, when we jump to the subarray ij, a lot of things can happen. We will definitely have A, B, C, B, and the new character nums of j, which could be anything. Can you check in constant time that this subarray is going to be a palindrome? Well, not really. Yes, we can check in constant time if the first character is going to be equal to the last one. This we can do. And let's say they are equal. Let's say nums of j was indeed the character A. Now, they are equal, but we still don't know about the rest of the characters, right? In this scenario, yes, B equals B and C is the middle character, so this is going to be a palindrome. But how should I know this without checking? Remember, the only information that I have is that the previous subarray is false. So I don't know whether this was ABCB or could have been, for example, ABCX. So here I also had an X. So for this example, this was not a palindrome. My point is that if you think about the general scenario, where let's say we don't know the values of the characters, right? Let's say this is I, this is j-1, right? So this is the previous subarray that we know if it is a palindrome or not, and this is our new character s of j. In order for our subarray s of I and j to be a palindrome, first of all, the first character should be equal to the last one. So yes, we can check in constant time if this one is equal to this one. And let's suppose they are. This is not enough. I still need to know if this substring is also a palindrome. Think about it. This one is equal to this one. Then this one should be equal to this one to this one, and so on and so forth. So this substring also needs to be a palindrome. And we don't have that information, unfortunately. All we know is whether the subarray s of I and j-1 is a palindrome or not, because we have checked it on the previous iteration, but we don't know about this subarray, I plus 1 and j-1. And this is an information that we will have to compute also using a linear approach. Checking this with this, checking this with this, checking this with this. So unfortunately, the optimization that we have used when solving problems in the arrays chapter, where we knew that only one new integer or element is being pushed to the subarray, is not so useful here. If we know that s of I plus 1 and j-1 is a palindrome, and we also know that s of I is equal to s of j, then we will know that the substring s of I and j is a palindrome. So instead of this order that we have right now, from checking the subarray ij-1 to checking the subarray ij, if we can change it to this, from the subarray ij, the next one that we are going to check will be the subarray i-1 j plus 1, then we can make this transition in constant time. And why is that? Very simple. We are going to know, after checking this subarray, whether it is a palindrome or not. And if this subarray is not a palindrome, definitely this one is also not going to be a palindrome. So, from false, I also have a false, right? And again, think about this. Let's take a subarray ij. Let's say the subarray ij is A, B, C. This is definitely not a palindrome, right? Then when we are going to have another element on the left, s of i-1, and another element on the right, s of j plus 1, they even might be equal, we still won't have a palindrome, right? Because this will not be equal to this. But if this is a palindrome, so this is true. So let's take, for example, ABA. Let's say the substring s of I and j is ABA. When we have another element on the left and another element on the right, there are two possible scenarios. They are either equal, which will also make this substring a palindrome, because these two are equal, and because we know this is a palindrome, all the other conditions are satisfied, or these two can be different, for example, x and y, and of course we know for sure, because the first and the last characters are different, that this is not going to be a palindrome. So, if this is a palindrome, and the new element on the left, which is s of i-1, equals the new element on the right, which is s of j plus 1, then we definitely have a true. So for this problem, we are not going to try out each and every subarray in the manner that we are used to, which is increasing by I and then increasing by j. We need to do this in a smarter way, such that each time we move to a new subarray, I gets decremented and j gets incremented. And what I'm going to do next is first try out each and every subarray of odd length, and then each and every subarray of even length. So let's start with the odd length ones. Alright, I've taken an example here, a string of length 5. We don't know the characters and we don't even care about that because the indices are important. Now, what are the substrings of odd length here? We have substrings of length 1, S0, S1, S2, S3, S4, of length 3, this 3, and a length 5. First, I want to tell you that what is special about strings or substrings of odd length is that they have a middle character, right? Let's take a look. The ones of length 1, of course, the middle character is the only character. For length 3, we have middle character here S1, middle character here S2, middle character here S3. For length 5, we have middle character here S2. And of course, if we have something like length 2k plus 1, because this is how an odd length, an odd number looks like, we are going to have S0, S1, and so on and so forth. Sk minus 1. This is going to be the first half of the substring of length exactly k. Then we have the middle element, which is sk. This is the middle element. And then we have the other k characters, right? From sk plus 1 all the way to s2 cross k. And here we have also k characters, right? This is very important. An odd length substring has a middle element and also a length which is determined by this number k. What this means is that I can iterate through all the substrings of odd length just by fixing these two, trying out each and every middle character from the string s and trying out each and every k, or the total length is not important. Let me show you in this example. First, I'm going to iterate through each character in my string s and set it to be the middle character of the odd length substring that I want to try out. And I'm going to start with S0. Let's suppose this is the middle character. Now, I can have k equals 0, so the length is 1, which means this is my substring, S0, here it is. Then, I can have k equals 1, which means a substring of length 3. So besides the middle element, one element on its left and one element on its right. And as you can see, this is not possible because we don't have an element to the left of S0. So these are all the odd length substrings that have the middle character in S0. Now I'm gonna try out the middle character to be equal to S1. Awesome. K equals 0. This means a substring of length 1. So only the middle character, S1. Awesome. I've taken it into account. Then I can try out K equals 1, which means length 3. So one character to the left and one character to the right, which means one to the left S0, one to the right S2. So S0, S1, S2, which is here. So I've taken also this into account. Then I can try out K equals 2, which means length 5, 2 to the left, 2 to the right. It won't work because I don't have two characters to the left of S1. Awesome. So I finished all the odd length substrings with the middle character in S1. Then I try S2. I try out K equals 0. This means I only take S2 into account. Here it is. K equals 1. This means one to the left, one to the right. So S1, S2, S3. Here it is. And of course here I can even try K equals 2. 2 to the left, 2 to the right, and I have them. So it's gonna be obviously the whole string. And here it is. And then K equals 3 is too much, so we will stop. Then I'm gonna try out the middle character to be equal to S3. K equals 0. Only the substring S3. Here it is. K equals 1 is gonna be one character to the left, one character to the right, so S2, S3, S4. Here it is. K equals 2 doesn't work because I don't have two characters to the right of S3. And lastly, I'm gonna set the middle character to be S4. K equals 0, I have only the substring S4. K equals 1 doesn't work. So as you can see, by trying out each character in my string to be the middle character, then trying out each possible length of a substring that has the middle character there, which I do by setting only K, because I knew the length is 2 cross K plus 1, I have tried out each and every substring of odd length. And you're probably asking yourself, why do we do this? Why do we need to set the middle character and then set the K when we can also traverse each substring of odd length with that previous approach and just check if the length is odd? Yes, but in this way, by first fixing the middle character and then just incrementing the K, you can notice that what happens is that we start with a substring of length 1, so I equals J, and each time K gets incremented, I is getting decremented and J is getting incremented. So basically we always add one element to the left and one element to the right. And this is exactly what we wished for. And in this manner, all I need to do when moving from a substring to the next one is just check if the new element on the left is equal to the new element on the right. And because I know that the previous substring was a palindrome 1, this one is also going to be 1. So let's see how the code looks like. And here we have the code that counts how many odd length palindromic substrings there are. Pretty simple. All I do is first fix the middle character. So I'm gonna try out each and every position from 0 to n-1. And once I know that position, as you can see, I don't do anything crazy with that K because the code would have been looked way messier. The simplest way to do this is to use our two pointers, I and J, which store the start and the end points of our odd length substring. They are both initially equal to mid, and while I is greater than or equal to 0 and J is less than n, and they are also equal, this means that this substring is definitely a palindromic one, so I'm gonna increment my answer, then I'm gonna jump to the next substring, which is one element to the left and one new element to the right. So I gets decremented and J gets incremented. I also check that and do this until I find the first palindromic substring which is bad, because of course if that is bad I know all the next ones are also going to be bad. And that's it. As you can see, the time complexity of this code is definitely big O of n squared. We have this for loop which does n iterations, we have this constant, we have this while loop which does at most n iterations, right? We can't decrement I and increment j for more than n times. So at most n here, and of course these are constants. So I have big O of n squared time complexity and big O of 1 extra memory complexity to find out the odd length palindromic substrings. Now let's see how to find the even length ones. If let's say this is my string, it has 6 characters, and I want to take an even length substring, I don't know, let's say I take this one, S1, S2, S3, S4. Obviously, this one is not going to have one middle character anymore, but it's going to have 2 of them. And S2 and S3 are the middle characters. So the only thing that we need to do here is instead of first choosing the middle character, we are going to choose the middle characters. And of course, the middle characters are going to be consecutive ones, so their positions will be represented by a pair of consecutive numbers, mid and mid plus 1. So yeah, all I need to do is still try out each and every value of this mid, like we did here, but mid now should be less than n minus 1, so I make sure that mid plus 1 also exists, and then, of course, same spiel, we start with those 2 characters, we make sure that they are equal, right? So we have a palindrome, and then we move 1 element to the left and 1 to the right each time until we hit the first bad substring. Let's see how the code looks like. Boom! And that's it. Only 2 differences in the code. As I've told you, mid now is at most n minus 2. I will be equal to mid initially, but j will now be equal to mid plus 1 initially. So we always start with 2 consecutive characters, I and j, right? And then all we do is that as long I is greater than or equal to 0 and j is less than n, and these 2 are equal, what do? Move 1 to the left and 1 to the right. This is I, this is j. If they are also equal, move 1 to the left, 1 to the right, and so on and so forth. Obviously, this is also big O of n squared time complexity and big O of 1 extra memory used. And that's it, guys. What I want you to take from this lesson is that there will be problems when we will have to try out each and every subarray or substrings and then find an information for that subarray or substring. And we can start with a brute force approach and optimize the algorithm based on the fact that when we want to compute the information for a substring, we have already computed the same information for other substrings, but there will be problems like this one, in which in order to take advantage of this thing, you will have to change a little bit the order in which you traverse the substrings. For example, here, the traversal that we are used to, in which we always increment j, so we add a new element to our current subarray, was not useful. What we need to do is add a new element to the left and a new element to the right, so we were able to check in constant time if the new substring is indeed a palindrome 1. And in order to do this, you are going to change the structure of your algorithm. For example, here, we don't have 2 nested for loops anymore, one for I and one for j. We have 1 nested loop for the middle character and then a while loop in which we have 2 pointers. Awesome, guys. This was it. I hope you enjoyed it, and I'll see you on the next one. Bye.